So in the previous example, we wrote our own simple thread pool system, and we discussed how it's only worth using the threading if we get beyond a certain threshold, because it actually becomes a lot slower. In this demo, we're going to still do some more threading. This time I'm going to use a different library for threading, and in particular we're going to use the Intel threading building blocks and the Parallel 4 algorithm that it supplies. Now, I've installed this via VC Package, which is what I use for doing most of my installs of software. And it's a really nice library, and it has far more than just this simple thing that I'm doing. And I thoroughly recommend, if you want to get into more multi-threaded, multiprocessor programming, to look at the Intel threading building blocks library. Now, the first thing you'll see is there's actually a fairly efficient update going on here. So there's some slightly better load balancing and generating of the threads going on here than there was before. And again, this should scale nicely. So once we start using larger amounts and blocks of data, we should begin to see that this app is going to start doing a lot more work and lose a lot more threads. So you can see that quite easily doing 1 million particles. My buffer and texture updates are quick. You can see CPU load is really nicely going there now. The threads are more persistent. So if you looked at my previous example, I was joining each time. The threads seem to be created and destroyed. TBB obviously is far more efficient, and it seems to be doing something, whereas my threading is not being created and destroyed or so on. I'm not entirely sure what that is. We'll just look now at my threaded version and the TBB version. We should sort of begin to see those sort of differences popping up, hopefully, and we'll also see that the TBB version is slightly more efficient than my version once it started running. I'm going to start running. May begin to run out of resources on my machine here, which does happen from time to time when you're doing this sort of stuff. There we go. So yeah, you can see it's taking a lot longer there now. So you can see the updates there. This is far more efficient. This seems to be working, and you can just see that from the TBB update and the threaded update. If I look both those at the top there, the core difference is that persistent amount of threads in the TBB one, whereas mine's creating and destroying threads each time. So that it's just added that little extra bit of efficiency. What's even better is the code used to generate this. We hash include, in this case I'm just using the TBB Parallel 4 algorithm. So we include TBB Parallel 4, and when I want to do my update, it's this very simple line of code. Again, it's a nice Lambda bit of code. So TBB Parallel 4, here's the blocked range. So the block ranged is, again, a template that's saying I'm starting at 0, I'm going to a certain thing. That will partition our data there, and I is the beginning of the range, the end of the range from this lambda that's captured in here. So the block range is passed into this, and it will then call update particles on those elements of the range as we go through. So incredibly nice and simple, and it's a bit like the hash pragma Parallel 4 that comes with OpenMP, just slightly more code there. But as you can see, it's nice, it's simple, it's a very easy win when we've got these nice, naive, simple updates that need to happen, that we can just fire them off in one of these, try and get our CPU to do a lot of work. And you can see this does scale particularly well when we run it now. We can go through and we can start seeing that we're doing a lot of work, and we've got a lot of utilization. The only other thing now is our texture buffer is quite a bit of work going on there, and our update is still quite a lot of work, and that's taking a big chunk of our time in our code. So we're going to now try and improve this even more. So the code that we're going to use is going to be based on this threaded update that carries on here. But our next step is going to be to look at how we can vectorize some of the mathematics that's going on here so that we are doing this using more efficient methods. And in particular, we're going to look at using SIMD instructions and the Intel intrinsics to do so.